So good morning. Welcome to Krishna's classroom. We continue to look at the characterization of completeness of orthonormal sets in a finite dimensional inner product space. So we assume V is a finite dimensional inner product space. Inner product space over this is the basic assumption that we are making. Now we have already seen that the orthonormal sets in V form a linearly independent set, and therefore the number of elements in any such orthonormal subset is less than or equal to the dimension of V. Now this is something that we have. Okay. So without loss of generality, we can assume that we have a finite orthonormal set, and we have the following theorem. If U is any finite orthonormal set, in an inner product space V, then the following conditions are equivalent. So let us list them out. Okay, equivalent conditions. Now the first condition is the orthonormal, or first statement is the orthonormal set is complete. Now we give other equivalent statement of the completeness of the orthonormal set. The second statement is that if equal to 0 for I equal to 1 n, here U, the collection, that is orthonormal set that you are considering. Then the third statement is the subspace span by U V. The fourth statement is if belong to V, if V belongs to V, then V can be represented as sigma inner product of V with Ui. That is an expansion of the vector in terms of the vectors in U is possible. The fifth statement is if V then Parseval's identity, then what you have is that VW, the inner product of VW is equal to summation over I W. The sixth equivalent statement is this. If V belongs to V, then what we have is that norm of V square equal to now the remark gives the Parseval identity. And of course 6 is essentially the generalized Pythagoras theorem. 6 is essentially so that's the remark that we make. So U is the collection U1, U2, etc. UN, and you know that it's assumed to be an orthonormal set. Now we are now talking about what is called the completeness of this orthonormal set. Okay, so we have 6 statements and each one implies the other. Therefore, they are all equivalent. Okay. So these 6 statements are all equivalent. If you assume any one of them this all others are true, which in turn tells that complete orthonormality of U can be used in any one of these forms, and that's the important part. Okay, so in mathematics it is often what we do is we give a certain define something, and then quite often we prove theorems or results which are equivalent to this. The objective of proving such equivalent results is to get the statement or get the result in a more, or the definition in a more applicable form, more convenient applicable form. Okay, so in any one of these forms, completeness of U can be assumed. Okay, so let us prove this one by one, and usually, I mean, this is a very typical, usually the strategy is to go in a cycle, as we shall do it here. So the proof is developed as follows. We assume 1, then we prove that 2 is true. Then assuming 2, you prove 3. Then you prove, assuming 3, you prove 4. Then assuming 4, you prove 5. And assuming 5, you prove 6. And then assuming 6, you prove 1. So you go in a cycle. So 1, 2, 3, 4, 5, 6. Sometimes it is more convenient to break this up into two such cycles, and then you may be proving 1 implies 2, 2 implies 3, 3 implies 1, and then probably to assume any one of this and then prove 4, 5, 6, and then 6 implies 4. So you prove these things in different forms. So that depends on what is convenient. Okay, right? And where the proof becomes transparent and simple. So let us start working on this. So this is the strategy. Okay. So first we assume 1. Assume 1. What is the assumption? The assumption is that U is orthonormal set. U is. What do you mean by that? It means that it is maximal. Maximal means what? It cannot be a part of a larger orthonormal set. Okay? So it cannot be a part of a larger orthonormal set. Okay? Or if say U prime is another orthonormal set such that U is contained in U prime, then U is equal to U prime. So this is a maximal orthonormal set. I mean, there are several orthonormal sets possible, several complete orthonormal sets possible in a inner product space. So what we say is that this is a complete orthonormal set. Now this means ONS stands for this is the short form that I am just using this. Okay, right. So assume 1. U is, that is, U is a complete orthonormal set. Then suppose V belongs to V not equal to 0, then is a unit vector. And assume is orthogonal to U. That means the inner product of V by norm V with Ui equal to 0. That is now what do? You take this vector. Now consider then what do you have? Then U is not complete because is an orthonormal set containing U. Now this is a contradiction. With the assumption that U is complete. Hence, if V is a vector such that okay. So if there exists a non-zero vector with this property, then certainly your given set is U is not complete, which implies if U is complete, that is U is complete, that is 1 implies 2. Okay, so that completes the proof of the statement 1 implies 2. Now we assume the statement 2. Then we prove that the subspace span by U is V. Okay, let me retain the statements there and prove each one of these statements. Okay, so let me do that. I use this space for the proof. So we have proved this part. Now the next assumption is that we assume 2 and then prove that 3 is valid. Assume 2 prove this. That is equal to 0. Now what we claim the span of is equal to, okay. Now again we use a method of contradiction. So suppose U is not equal to span of not equal to, then there exists V belonging to V such that V is not a linear combination of UN. Then what we have is this. If we define V prime to be V minus sigma UI, then this is not equal to 0. Okay? Because you see that any linear combination of V can be only in terms of U1, U2, etc. If there is a linear combination, it has to be like this. Take this, okay. And what does this mean? And by the previous theorem that we have proved, V prime is orthogonal to U. Okay, V is not equal to, V prime is not equal to 0, V prime therefore hence it follows that V ui equal to 0. Okay. there exists v prime not equal to 0, this is a contradiction, okay, right? However, this contradicts assumption. Hence, the span of u is not equal to v, equal to v. So that completes the proof of 2 implies 3. Now let us prove 3 implies. So at each stage we are but it has to be clear about what we are assuming and what we are trying to prove. Okay. So this we have proved. Now we assume this. What is 3? Statement 3 is that u, the span of u is equal to v. Then what we assert is that every v belonging to v can be expanded in terms of u1, u2, etc. un. Okay, so let us prove that. Assume 3, that is span of the orthonormal set u is equal to then we claim that is v can be okay. Now span of u equal to v means, so v belongs to v implies v belongs to, which implies v is equal to a linear combination of vi. Now let us compute this. Which is equal to alpha I j, which is equal to where J delta ij is a Kronecker delta, and this essentially gives you alpha, which implies V equal to, okay, equal to sigma so that completes the proof of 3 implies 4. Now let us prove 4 implies 5. Okay. So we have completed the proof of 3 implies 4. What does this mean? This means that any V in V can be expanded. That is the assumption that we are making in terms of U1, U2, etc. UN in the given form. Okay. So we prove next 4 implies 4 implies 5. Okay, let us assume that is for belongs to V, V is equal to if you want, you can write here J, because it's a dummy variable anyway, and write this J. Now let us take the inner product of V with W. This is equal to UI uj. Okay. Now you see that UI uj is equal to, so therefore we have delta I. That is the Kronecker delta. Now when I equal to j, this is 1, otherwise it is 0. Therefore this is equal to right? Here, conjugate. So that completes the proof, and this is what is called the Parseval's identity. Now we prove 5 implies 6. That's quite simple. Just one line. Now you assume 5. That is now set. V square equal to So that completes the proof, and this is essentially your Pythagoras theorem. Okay. Now what remains to be proved is that 6 implies 1. That completes the proof of the entire theorem. Now we prove 6 to complete the cycle. Okay. So we assume 6. That is norm of That is what we assume. So if U is contained in a larger orthonormal set, say UN, then we such that that is U naught is orthogonal to therefore let us take U naught square. If 6 holds by 6, but it implies norm of which in turn implies, so we have U naught, inner product of U naught with U naught is equal to 0, therefore U naught is equal to 0. So that we cannot have such a larger set with a non-zero U naught coming here. Thus complete. So that completes the proof of this theorem, and these are the various equivalent forms, and one can use any one of them and choose that as the definition. That's the advantage of proving such equivalence theorems, and if you want to use, wherever you want to use the completeness of U, any one of these statements is equivalent to that, and maybe in certain problems it may be easier to work with one of these assumptions. Now let us look at some of one of the most important consequences of this result. Now this is what is called the Schwarz's inequality. Okay, but before that I want to make a remark. Let us look at this, the statement 6. The statement 6, now I think I can take out this here. Okay, you look at this. In R3, suppose you take the standard basis is a complete orthonormal set. Now what one does is this, we use small. Okay. Now you see that if you choose an x, suppose you choose an x belonging to, then what you have is this. This is your E1. This is E2, E3. Now you choose any vector. Then you see that now this is what you call, this distance is E1, and this distance is xe2, and this height is so these are three vectors: x e1 e1, x e2 e2, x e3 e3. These are the orthogonal projections of this vector to say the space span by e1, the space span by e2, the space span by e3. Okay. Now, so we have, therefore, what is the, so if you look at this box, okay, the length of x dot x, or x inner product with x, the usual inner product, is the length of this, and that is equal to sum of the squares on this side. So in this case you see that this is the Pythagoras theorem for the parallelepiped that you have. Okay. So you can think of a box of something like this. This is the box, and this is the diagonal, and these are the edges of the box, and you see that's a rectangular parallelepiped, and the diagonal is given by the sum, the square of the length of the diagonal is given by the sum of the squares on the sides. That's the particular result. That's why I said it's a generalization of the Pythagoras theorem. Okay. Now let us prove the famous Cauchy-Schwarz inequality. See, in R3 or R2, this is essentially the statement that mod cos theta is less than or equal to 1. Let us see how this comes about. Yeah. So let us first prove this here, or give the statement and then prove this. It's a very important inequality which has lot of applications when it comes to the study of inner product spaces. Is less than or equal to now this is the Cauchy-Schwarz inequality. Now let us prove this theorem. Prove this theorem if V equal to 0, then what happens? Then you see that the either side, then UV equal to 0. Therefore, this inequality is trivially true with either side becoming 0. You get 0 equal to 0. So let us assume V is not equal to 0. See, the same statement holds with U also equal to 0. If you take U equal to 0, the same statement holds immaterial. Right. So we can assume both U and V are not equal to 0. At least for our purpose, for the time being, I think we need only assume that V is not equal to 0. Then you look at this V divided by norm V. V divided by norm V is an orthonormal set. Now just apply Bessel's inequality by we have what does it say? It says each U There is only one term in this. Okay. Therefore, this is what you have. Okay. Or in turn, so this implies this is the proof of this inequality. So it comes out at one stroke from the application of the Bessel's inequality. Okay, so that completes the proof of this. Okay. Now the question that you have to ask, okay, what is this? This is, if you look at, okay, so you take R3. So you have again the same kind of picture that you have. This is X, this is Y. Suppose this angle theta. Then what you have is that suppose X is equal to then you see that the Bessel's inequality, or sorry, the inequality that we have written here is this, that is X, Y, assume both X and Y are not equal to 0. Then what happens? Then what is this? This is actually, that is modulus of so what does this mean? This is actually the dot product of these two vectors, which is essentially the length of this. Okay, so this is the, but this is equal to, as we have seen earlier, this is equal to sigma theta. This we have seen. Therefore, what do you get? So you get, this implies less than or equal to cos theta is less than or equal to 1. From which you can see when see, you can actually show that equality holds. So in the Cauchy-Schwarz inequality, the equality holds whenever V is a function, V is a scalar multiple of U. If and only if U is a scalar multiple of V. I mean, that's quite easy to see when one way. The other way, you have to work out. So proof. Now, what are the important consequences of this assumption? Now, this is a tool to prove that what we have defined has the properties, or what we have defined as norm has the properties of a length function. Okay, so we prove the following. Define square of the norm of, then this essentially corresponds to the length that you have. That. So what we want to prove is that it has all the properties of a length. Okay. So what are the properties of a length? So length function, what you call norm. Okay. So let V be a vector space. A length function is, or let me use the is a real valued, a non-negative the following properties. We are working on a vector space, so you have two operations, namely addition and scalar multiplication. So we one norm of V, this is what we have said, it's a real number, and norm of V equal to 0, that means all non-zero vectors have positive length. 2, norm of alpha V will be quite clear. If you take V alpha to be real, what happens? You are just in R3, for instance, you are just elongating the vector by, it's a scaling factor. Okay, so if alpha is negative, then you are reversing the direction, but still, scaling it in the opposite direction. And what we have is that the modulus of alpha times the length of V. The third property is this is the triangular inequality. This is what we have, the following. See, you have U, V, you use the parallelogram law, and this is your, okay, this is V, W, this is V plus W. V plus W is this vector. What we are asserting is that, so this, you apply the parallelogram law, then you see that the length of the diagonal is less than or equal to sum of the lengths of the sides, namely norm V, and this is also the length of this is the same as the length of this by parallelogram, by the properties of the parallelogram. And you see that this is true. Now, I just want to make a remark here. The remark here is the following. Now, you see, V is a vector space with a structure endowed by the two operations, namely addition and scalar multiplication. Therefore, if we are defining this function, you have to say how it works on these vectors, because what are the operations, how it goes, how the operation interacts with these two operations, namely scalar multiplication and addition. So this, the property 3 that you see, which you call the triangular inequality, is a statement on how it operates, how the function, that is the length function of V plus W, is less than or equal to the length of V plus the length of W. Okay, so on sum how it works, then on scalar multiplication how it works, and how it is related to the value of the function for V, and this is what you are saying. So here you are, how is the length of V plus W related to the length of V and length of W? Now this is mandatory. Okay, mandatory in the sense that once you have a property, a structure on the space, and you are bringing in a new thing, you have to immediately make sure how it interacts with the prevailing structure, and that is important. You will see this coming everywhere. I think we have done it for the inner product. Inner product is a map from V cross V to C, and we said a few things about it, namely whatever the, so if you look at the inner product, see, inner product is a map from C. So what all things we stated the following. said that V suppose you interchange them, what happens? This is what is called a conjugate symmetry. Then we had this property. So what we are saying is that how the interaction of alpha v beta u, when you take the sum in this place v as the sum of two vectors, then how this function, what is the image of the, see, you are asking here, this is the image of v, the ordered pair vw is mapped to. So you are asking how alpha v plus beta w comma beta u w is mapped to what? Symbolically this. But how is it related to the image of vw and the image of uw? Okay, that's what we have described there, right? And then you have this, okay, so this is what is significant, and of course the positive definiteness. So we have v, that's additional property there. Okay, so you have this. So how you have to immediately say how it is going to work on the prevailing structure that you have. Okay, right. So that's a remark I wanted to make. Now you see, what I want to say is that this is a length function. The inner product induces yeah. So you see, you have to verify all these properties. What do you have? Okay, so there is the inner product. So we have V with inner product. This is the inner product space. And inner product, you know, is a map from V cross V to C with certain properties. So we use that to show that you have a length function induced on V. Okay. So define you know that this is well defined because we have inner product of V with V is greater than or equal to 0. Therefore, this square root is well defined. Okay, now we show that this is a length function. Obviously, by definition, and norm of V and by the definition of the inner product, and when V equal to 0, automatically the norm V is equal to 0. Okay. Now this is the basic definition. Right. Now what is there? So the first property is verified. Now look at this. By definition, this is equal to square, which implies so the second property is verified. Now we come to the third property. So the third property is we have to use this and this let us expand. This is equal to conjugate plus this is equal to and this is obviously less than or equal to now this part, you see, the real part of the inner product of U V with the W is certainly less than or equal to the modulus of the inner product of V with W. Okay. So this is less than or equal to and this is now we can apply Cauchy-Schwarz. Now this is equal to norm of V plus norm of W. Therefore, what do we have? So if you put this together, what do you get? You get the third property, namely norm of v plus w is less than or equal to norm of v plus norm of. Therefore, so that proves the third property. Hence, which is what is called the length function. This is called the norm. It's called the norm of V. So that proves that the inner product induces concept of length for each vector on a vector space, if it is an inner product space. Okay. Now what next? Now what you can show next is that this induces a concept of distance in the inner product space. Okay. So define. So in fact, it is done by, you see, the important point is that there are different ways in which possibly one can introduce the length concept. But the one that comes from an inner product is something very special. It can be called the Euclidean length, if you like. Now you see that, so we define distance between define it as norm of. Now you see that since both u and v are vectors in V, u minus v is defined because it's a linear space. Now u minus v is a vector in V itself, and for each vector in V an inner product is defined, and the inner product induces what you call a norm. Okay, so we want to show that D is a distance function. So what are the properties of the distance function? So if you have a set, take two vectors v and w. So the distance between v and w from v to w is the same as the distance from w to v. Okay, so let us write down that. So what we want is this, verify this. Before that, I think the distance function has to be non-negative. These are the desirable properties of the distance. Now what more you want? You want third property, the symmetry. And the fourth property is d of less than or equal to this triangular inequality, d of these are the properties. So the distance from v to w is less than or equal to distance from v to u plus the distance from u to w. That's the third property that you have. Okay. The second property is that the distance from v to w is the same as the distance from w to v. The usual our intuitive notion of what you call the distance function. The distance function is a real valued function. So what we assert is that this has all these properties. It's quite simple. Now it is quite simple once you have this inequality. So what is that you obtain here? Okay, our definition is and the first thing that you have to prove is that this is possible. Okay, now you know that norm is positive and norm of that is u equal to v. Okay. So d of which is equal to so plus minus 1. Okay, so the final property is this. which is less than or equal to, from the properties of the norm that we have proved earlier, therefore that proves the triangular inequality. Hence, is a symmetric space. So the inner product induces a length concept on the space, and that is actually what you call a metric space. Therefore, now you see the inner product space has a topology defined on this. So you have the algebraic structure, and through the inner product we are inducing a topology on this. Okay. Now you have the algebraic structure, you have the topological structure. Two structures are different, and what we are looking for is how these two properties interact, and this is what we are going to do next time. Okay, thank you very much.